Hey, workshop students. I got a question here to help out on another projectile one. So you guys are getting started here with your two-dimensional motion. Let's read this one. Here it says, a cannonball is fired up a hill with a launch speed up. So let's take this as the bottom of the hill, and the hill kind of angles up. And it says it's fired with a speed of 98.3 meters per second at an angle of 40 degrees above the horizontal. So it's going to do something like this and presumably land on the hill somewhere. The hill is tilted at 20 degrees. So let's see. This angle here is 20 degrees. But the big angle, if I can squeeze it in here, and maybe I'll do 20 twice. Maybe that'll be a little clearer. All right, so we've got 20 degrees for the hill and another 20 degrees beyond that, so a total of 40 degrees, because it says 40 degrees above the horizontal is our firing angle. Okay, and so maybe I'll just point to it, 40 degrees. Okay, the hill is tilted upward at 20 degrees above the horizontal. The cannonball lands at a spot on the hill, which is a distance d up. Okay, so somewhere along the length of the hill is a distance d. Solve for this distance d. All right, now, if there's anything I can help you with, it'll be the same hint that I gave on the last projectile one. You'll want to ask yourself for all these problems at the very beginning, is this a constant acceleration problem? Because if it is, we can use those constant acceleration equations. And this is. And so I can do the equations. The other little hint I like to give you is ask yourself, is this, a two-dimensional type of problem? Where then we can do the x-axis and the y-axis. And so a nice little skill, I think, is to take your paper and divide it in half. And then maybe up above you can say, okay, the acceleration in the x direction is 0, and the acceleration in the y direction is negative 9.8. And of course, meters per second squared would be the units. But since that's what it does, and doesn't say ignore air resistance, but I think that's implied. And it says it's a cannonball, so it's not like a rocket, so it has other accelerations going on. This is purely just a acceleration because of gravity. And that's kind of the lesson here, that the acceleration due to gravity is negative 9.8 in the vertical direction and 0 in the horizontal direction. And the same thing that I said in the other projectile one, let me say it again, maybe the best information I can give you is the way you're going to do these types of problems is you're going to do one-dimensional motion twice. So yes, it is harder because you got to do it twice, but it's really the same thing you learned in the last week. So that's really the lesson here. And so I can write out my two equations for the x. Those were final velocity in the x direction is equal to initial velocity in the x direction times acceleration in the x times t. That's our first equation of constant acceleration, and this is a constant acceleration. Our second one is final position is equal to initial position plus initial velocity in the x direction times time plus 1/2 acceleration in the x times squared. So that's what I would do first. I would just write that out for the x direction and also write it out for the y direction. So final velocity in the y direction is equal to initial velocity in the y direction plus the acceleration in the y direction times time. Because again, remember, that equation is valid if you have constant acceleration. And we do. It's negative 9.8 in the y direction. And we also have constant acceleration in the x direction. And of course, the other equation, which matches here, that's why I keep saying, well, I'm just going to do the same thing twice. I'm going to do a set of equations for the horizontal motion and a set for the vertical motion. Okay. And I'll just write it out. And that's what I have so far. I have convinced myself that I have two-dimensional motion. That's why we got two columns. And I've convinced myself that they are constant accelerations for each case. This one is 0 in the x direction, and this one is negative 9.8. That's why I've justified those equations. I could even go one step further and take those two equations and put in my acceleration of 0. So this would say final velocity in the x direction is equal to initial velocity in the x direction, because that one would be 0. And that one's kind of boring, but what it means basically, though, is it doesn't change its speed in the x direction. Exactly. That's what 0 acceleration means. And then this one here would say final position in the x is equal to initial position in the x plus the initial velocity in the x times time, and then plus 0. So for this particular problem, I have taken and gotten to this point that these would be my two sets of equations to use for this problem. And I could do the same thing in the y direction, if you will. I could say that the final velocity in the y direction is equal to the initial velocity in the y direction minus 9.8 t. So when I put in that acceleration, and then same thing here, this would be final position in the y would equal initial position in the y plus the initial velocity y times time. And then right here, where I have a 1/2 times the acceleration is a negative 9.8, so that becomes a negative 4.9 t squared. Okay. Now, this, of course, is 4 equations, and it so far has nothing to do with the slope of the hill. But let me hold off on the hill and the slope of the hill. That's got to come into play at some point. But let me just use this second one, which has to do with position, and then this one here, which has to do with position. And, of course, now is finally a time to make a decision. Where do you want to put your grid? Where do you want to put your origin? And I'll draw it in green. The most common place to put the origin is where the ball launches. And the one I was doing with the keys from the balcony, that one I could have gone either way. I could have picked at the balcony, which I did, or I could have picked down at the ground. Would have made logical sense too. This one, I think the only other choice we really have is where it lands, and I don't think that's very inviting, so I'm not even going to discuss it. I think really the only place to pick the origin is the launch point. And usually that's the best place, not all the time, but it has a significant advantage in that the initial position in the x and the initial position in the y now become 0. So this equation here becomes final position x equals initial velocity x times time. And this one here becomes final position in y is equal to initial velocity y times time minus 4.9 t squared. So we start with this general idea, and as we begin to apply it for this problem, including this grid, we've boiled down to this one involving distances. And I picked the ones with distances since that's what's going on in this problem. Now, also involved here are the initial velocities. So let me talk about that and bring you back I guess it's 2 chapters, because if the total speed is 98.3 and it's being launched at 40 degrees from the horizontal, we could take our vectors and break it down into components. This was the whole lesson of Chapter 2. And I got to admit, Chapter 2 sometimes can seem a little abstract at the beginning, because you're like, well, why am I doing all this? But I hope now you begin to see why you're doing all this. You're doing all this because in order to work out this problem, you have to put x's with x's. And so you have to figure out how much of this velocity is actually in the x and how much of the velocity is in the y. And that's where we can write down the cosine of 40 degrees. Because it would be this adjacent piece, which is I would call the initial velocity in the x. So it would be initial velocity x over the 98.3. So the initial velocity in the x would be 98.3 times cosine of 40 degrees. Okay. Now, likewise, if I put the sine of 40 degrees, so the sine of 40 degrees would be opposite. So that's this leg. And that is what I would call the initial in the y direction. See, because what I'm trying to do here in this picture is to show you that the initial x plus the initial y, so these two together, is this initial velocity. So I'm trying to figure out from this initial velocity how much is initial in x and how much is initial in y. Because that's what I need. And so the sine of 40 is opposite over hypotenuse, meaning that the initial in the y is 98.3 times the sine of 40 degrees. Okay? And I will say, as you get better at these, you'll probably stop writing this step. You'll just go right to this step. You'll say, look, this is the magnitude, and I want the adjacent piece. So you go a cosine. Or you look at this one and you say, oh, I want the opposite piece. So you take the magnitude and you take the sine, because you want the opposite piece. And so you'll get real good, I hope, at just recognizing that I want adjacent piece, so that means cosine function. Or I want opposite piece, oh, that means sine function. Okay. Otherwise, you start burning too much brain power here, and you kind of lose track of these, especially when we get into the next chapter, where we start doing forces, and there's a lot of physics, and you want to leave your brain power to that, not on these components. So the sooner you can get a little more familiar with that, the better, but it's worth showing you. Okay, so now let me take this and put it into here. So this would say, okay, here's my equation. The final in the x direction would then be this 98.3 cosine 40 degrees t. And then over here, I would want final position in the y is equal to 98.3 sine 40 degrees t minus 4.9 t squared. Okay. Now again, let's talk about some strategies here. You can kind of see then, and maybe I'll just put a circle around it, I have two equations here and three variables, or three unknowns. One unknown is the x position, another unknown is the y position, but the third unknown is the time factor. So clearly two equations with three unknowns is not enough to solve this. So what else do I know here? Now, that might tempt you to go back to this equation on velocities that we never dealt with. But I'm not going to go too far with that temptation, because this number I actually do know down here. Okay, so there's nothing new there. And this number would be the velocity, when it lands. And yeah, that's another equation, but it just introduces another unknown, the velocity when it lands. And I don't want anything really to do with that. It didn't ask for it in the question. I don't need it to, so I'm gonna stay away from that one. So where is this third equation I'm gonna get? And of course, I hope you're saying to yourself, well, that would be something about the incline and the hill. We haven't done anything with this. Everything we've done would be true for any projectile. This has nothing to do with the shape or the slope of the hill yet, and that's true. So let's keep these two equations in the back of our mind here, but let's also write down something about the hill here. Okay. Oh, and it looks like I need a newer pad here. Okay. So let's say something about the hill. So the hill angles up, okay? And the hill has an angle here of 20 degrees. 20 degrees. Now, that could be interesting, because The x position is how far it went here. The y position is how far it goes up. So let me call that x final and y final. And then there's the d. So again, if you're getting used to your trigonometry, cosine of 20 degrees would be final position over d. And the sine of 20 degrees would be final position over d. And that means I can write final position x in terms of a d and final position y in terms of a d. So if I put those into here, I would have this things in terms of d. And so now I would have d and t. And I like that. So let me do that. So right here, this equation for final position, let me put d cosine 20 degrees. That has to equal, as we said, 98.3 times cosine of 40 degrees t. Maybe I should continue on this page 2 with my 2 columns. Okay, and then right here, this would be d sine 20 degrees equals, so that would be the final position here. And then this would be the 98.3. This would be then sine of 40 degrees t minus 4.9 t squared. Now I like what I'm seeing mathematically. I now have 2 equations with 2 unknowns. One is d and one is t. And the one we're asked to solve for is the d. Now, I think this would look better if we had some numbers instead of trig functions. So let me do that. Let me get out my calculator. Let me make sure my calculator is in degree mode, which it was, and I just changed it to radians. That was dumb. Okay. And so let me go cosine of 20 degrees. So this is saying 0.940d equals, and let me make a number out of that. That's 98.3, and let me multiply it by cosine of 40. So this would be 75.3 t. In fact, let me do one more step. Why don't I solve this for t? And so if I take this number that we got here and I divide it by that number, we are looking at 0.01248d. Okay, so that's a little easier to work with than all these trig things. So everything that I can convert to a decimal and combine, I've done. And so now I would say I have one equation with 2 unknowns, a d and a t. And I can do the same thing over here. Let me put in the sine of 20 degrees. So that would be 0.342d equals, and put in this number, 98.3 times the sine of 40 degrees. And so that would be the 63.19 t minus 4.9 t squared. Okay. Now maybe you begin to see why I was thinking, hey, let's solve it for t, not for d, because now I can put my t into here, and I'd have an equation that only has d, and then I can solve it for d. So I'm going to do that. So 0.342d goes there. 63.19 multiplied by t, and t is 0.01248d, minus 4.9, and then I have t squared, so 0.01248d squared. Let's see what that gives me. Maybe I'll put an equal here. This right here, the 63.19, when multiplied by the 0.024, gives me that number. Okay, so that many D's. And then if I subtract 0.342, I get 0.4465D. And so I'd be putting that together with that. So I did that and subtracted. And I did all that so I could move this to the other side of the equation and make it a plus. And so that number would be the 4.9 times 0.01248 squared. So that's going to be a 7.632 times 10 to the negative 4 d squared. Yeah, there we go. Okay, now I have a d on each side. So the trick to that is divide both sides by d. But remember, you can only do that if d is not the answer or not 0. So let's check. A d equal to 0 would work. Now, d equals to 0 is technically a solution here, and rightfully so, right? It crosses the hill at d equals to 0. That would be back here at the launch point. So it's not a surprise that it does cross the hill at d equals to 0. So d equals to 0 is one of the two solutions, but it's not the one we want. You know, does the projectile cross the hill at d equals to 0? Yeah, that's the bottom of the hill. That's where it started. So the one we want is the d that doesn't equal to 0. So that justifies us dividing by d, the one that's not equals to 0. And so then we would have this 0.4464, and we can then divide that by this 7.632 times 10 to the minus 4, and we can get a d of 585 meters. Yay! There's the answer. And maybe I should just say, there's got to be so many different ways to do this. I mean, I could have easily solved this for d and put it into there. I guess I could have way back here put the t and put it into there, and I had something with only x's and y's. And then I could have done something that said something like d squared equals to x squared plus y squared. That would have worked. I could have done that, actually done that first and then put in the x and y and then have d and t. There's just a lot of ways I could have gone with that. So I'm not sure which is the better of the ways, but this is the way that I kind of saw and seemed like a direction to go. All right, hope that helps.